Imagine a frozen moon orbiting Jupiter ... And one day, something cracks, a fracture in the ice, a sudden rush, and from beneath the surface, an entire ocean erupts into the void of space. What happens next? Would Europa survive? Or are we watching the silent end of an alien world, before it ever had a chance to speak? Chapter 1. A World Beneath Ice. Let's start with a place that, at first glance, doesn't look like much. Europa, just another icy moon, orbiting the gas giant Jupiter. Small, cold, and quiet. But underneath that frozen surface lies one of the most fascinating mysteries in our solar system. Europa is about the size of Earth's moon, yet it holds a secret that could rewrite everything we know about life in the universe. Its surface is a shell of water ice, cracked and scarred, like broken glass stretching across an endless plain. The ice is thick. Scientists believe it could be anywhere from 15 to 25 kilometers deep. But what's beneath it is what makes Europa so important. Beneath that icy crust, there's an entire ocean, a vast, global sea of liquid water. Not just pockets of ice and ocean that may be twice the volume of all the water on Earth combined. And it's not frozen. It's kept warm by tidal heating, a process driven by Europa's gravitational dance with Jupiter and its neighboring moons. As Europa orbits, the immense gravity of Jupiter pulls and squeezes it, creating friction inside the moon's rocky core. That friction releases heat, which rises up and melts the bottom of the ice, forming a subsurface ocean. So, even though Europa's surface is colder than Antarctica, the water beneath could be warm enough to support life, not just survive, possibly thrive. But how do we know any of this, if we've never drilled into the ice? Well, there are a few key clues. First, we've observed strange brown and red markings on Europa's surface. These lines, called lineae, are believed to be cracks in the ice, where warmer water from below may have seeped up, carrying minerals and other materials from the ocean below. Second, spacecraft like Galileo have detected changes in Europa's magnetic field, which suggests there's a conductive liquid layer underneath the surface, and water with dissolved salts. That's very conductive. Third, and perhaps most exciting, we've seen what may be actual water plumes erupting into space. These geysers, similar to those on Saturn's moon, Enceladus, could be brief but powerful blasts of ocean water making its way out through cracks in the ice. All of this points to one thing. Europa is not just a dead rock. It's alive geologically, and maybe even biologically. Let that sink in. A tiny frozen moon, over 600 million kilometers from the sun, may have the three key ingredients for life: liquid water, a heat source, and organic compounds. If life exists anywhere beyond Earth, Europa is one of our best bets. Now, here's where things get even more interesting. Because while this hidden ocean is protected beneath thick ice, it's not invulnerable. In fact, some scientists believe that if a major event occurred, like a massive asteroid impact, or even the buildup of pressure from inside Europa's ice could crack open, and when that happens, the ocean could escape. It might explode outward in a violent burst, spraying saltwater into the void of space, an entire sea, lost in seconds. But before we get to what that would look like and what it would mean, we need to understand Europa as it is now. It's easy to think of moons as lifeless, but Europa is incredibly dynamic. The surface is smooth in many areas, with very few impact craters. That tells us it's constantly being reshaped. In geological terms, it's young. The icy shell may move, shifting and flexing like tectonic plates on Earth. Some researchers even think there could be ice quakes, frozen equivalents of earthquakes. Europa might also have something like hydrothermal vents, just like the ones deep in Earth's oceans. These vents, powered by heat from the moon's core, could release chemicals that feed microbial life. On Earth, entire ecosystems exist around these vents without sunlight. That's important, because Europa's ocean is in total darkness. So we're not talking about sunlight-based life like plants or fish. We're talking about extremophile steamy organisms that live in the harshest conditions imaginable. And if such life exists, it's been hidden there for billions of years, shielded from radiation, protected from the vacuum of space, isolated in a world of salt, heat, and time. It's this quiet alien world, this vast ocean beneath ice, that makes Europa such a tempting target for missions like NASA's Europa Clipper. That spacecraft, launching soon, will orbit Jupiter and perform dozens of flybys of Europa. It'll map the surface in incredible detail. It'll analyze the composition of the ice, and it'll sniff the thin atmosphere for traces of what lies beneath. But even that mission can't drill through the ice. It can only watch, listen, interpret. The real answers, they lie deep below, in the pressure and silence. So now we come to the question, what if something breaks the ice? What if that ocean so carefully sealed away escapes into the emptiness of space? What would we see? What would we lose? And would it be the end of Europa's story, or the moment it finally speaks? Chapter 2. The Trigger. What could go wrong? Every world, no matter how silent or stable it seems, has its breaking point. And for Europa, that point might be closer than we think. So far we've seen Europa as a sealed worlder, frozen shell holding back an ocean beneath. But this balance, between ice and ocean, pressure and gravity, is fragile. All it would take is one trigger, one moment for everything to change. Let's imagine the possibilities. One of the most obvious and dramatic triggers is an asteroid impact. The solar system is full of wandering rocks. Some are tiny, no bigger than a suitcase. Others are kilometers wide. Most never get close to Europa. But space is unpredictable, and even a small asteroid, moving at tens of thousands of kilometers per hour, could hit with explosive force. If it strikes the right spot, say, a region already weakened by surface cracks or thin ice, it could penetrate deep enough to disturb the ocean underneath. The heat from the impact, combined with the sudden pressure release, could open a channel between the ocean and the surface. In that moment, Europa's secret would no longer be a secret. A geyser could burst from the moon's crust, spraying salt water and vapor high above the surface, maybe even into orbit around Jupiter. But an asteroid isn't the only way this could happen. Europa is already under constant stress from Jupiter's immense gravity. This force isn't steady, it changes as Europa moves along its elliptical orbit. At times, the moon is closer to Jupiter, and the gravitational pull becomes stronger. At other times, it's farther away, and the pull weakens. This constant stretching and squeezing, called tidal flexing, creates internal friction. That friction heats the moon's interior and causes its icy shell to flex and bend. Over time, these tidal forces can widen existing fractures or create entirely new ones. Think of Europa as a frozen balloon, constantly being pushed and pulled. Eventually, the surface may reach a breaking point, not from an outside impact, but from within. Now, combine this with something else: internal pressure. Under the ice, there's liquid water, but it's not just calmly sitting there. It's likely under intense pressure, especially near geological hotspots or areas where the ice is thinner. As pressure builds, it can force its way upward, seeking the path of least resistance. If a crack extends deep enough, that pressurized ocean water could shoot upward, just like a shaken bottle of soda with a cap suddenly opened. And there's one more possible trigger, that's harder to detect but just as dangerous: changes in the ice structure itself. Europa's surface isn't perfectly smooth. Some areas are covered in what scientists call chaos terrain, places where the ice seems jumbled, broken, and rearranged, almost like giant icebergs that have been shuffled around. This could be caused by ice melting and refreezing in cycles, weakening the structural integrity of the crust. Over time, those areas may become unstable. If part of the crust suddenly collapses, it could open a hole straight to the ocean. Any of these events, an asteroid, internal pressure, tidal stress, or structural collapse, could trigger a breach. And once that happens, the process could move quickly. The water wouldn't just bubble up. In the vacuum of space, it would erupt. The pressure difference is so extreme that water exposed to space doesn't stay liquid for long. It flashes into vapor, then rapidly freezes into ice crystals. You'd see a plump perhaps hundreds of kilometers tall rising from the surface. It might look like a fountain or a jet, surrounded by a mist of tiny ice particles. Under the right lighting, it could even shine with sunlight, forming a shimmering arc above Europa's horizon. And if the breach is large enough, or if multiple fractures open at once, it might not just be a single geyser. It could be a massive release, an entire region of the ocean venting into space. Some of the water might fall back to the surface as snow. Some could be pulled into orbit around Jupiter, creating temporary rings, and some might drift away, forming a cloud of water vapor and ice grains detectable by telescopes or passing spacecraft. But what makes this even more remarkable is that such an event might not be hypothetical. We've already seen signs of it. In 2012, the Hubble Space Telescope detected what appeared to be a plume of water vapor above Europa's south pole. In 2016, it happened again. The data wasn't 100% conclusive, but the signs are there. And NASA's upcoming Europa Clipper mission is designed, in part, to study these plumes. Its instruments will look for them during multiple flybys, hoping to catch one in the act. Why does this matter? Because if we can confirm that water from Europa's ocean is reaching space, it gives us a way to study the ocean without drilling. Imagine that. We could fly a spacecraft through the plume, scoop up water vapor, and analyze it for salts, minerals, even organic compounds. That kind of sampling could answer one of the biggest questions of all. Is there life in Europa's ocean? But it's a delicate balance. A single plume is a window. A full-scale breach could be a catastrophe. If enough water escapes, it could destabilize the ice shell. The surface might collapse inward. The ocean could lose heat. Over time, Europa's active geology could shut down, and its ocean might freeze completely. In trying to see the ocean, we might also be watching its last breath. That's the tension at the heart of this story. Europa is both protected and threatened by its icy shell. The same ice that keeps the ocean warm also seals it off. The same cracks that offer a glimpse could become the cracks that end it all. So the question becomes, are these events part of Europa's natural cycle? Or are we witnessing a slow breakdown, one that could, someday, lead to a true ocean escape? In the next chapter, we'll explore what that would look like in detail. What happens when an entire alien sea breaks free into space? Not just a plume, not just a crack, but the full release of a hidden ocean into the endless dark. Chapter 3. Ocean in the Void. The Escape. So now, let's imagine it really happens. A crack opens wide across Europa's surface, maybe triggered by tidal forces, an impact, or the slow, silent buildup of pressure from beneath. Ice fractures. Water, long buried beneath, finds a path to freedom. And then, in one sudden moment, Europa's ocean escapes. What would that look like? First, it wouldn't be a quiet release. The moment the pressurized ocean water hits the vacuum of space, everything changes. Space is a brutal environment, cold, airless, unforgiving. There's no pressure out there, no atmosphere to slow things down. So when that water bursts out, it doesn't just flow, it explodes. The water boils instantly. Not because it's hot, but because in the vacuum of space, there's nothing to hold the molecules together. Liquid turns to gas in a flash, and as it spreads outward, much of it rapidly freezes into tiny ice crystals. You'd see it if there is a massive, glowing plume. It might shoot hundreds of kilometers above the surface, forming a fountain of vapor, mist, and ice. Sunlight would catch the particles, casting a shimmering halo around Europa. From afar, it could look like Europa had grown a luminous tail, like a comet. But this isn't just a single geyser. In this scenario, the crack doesn't close, it widens. Pressure from the ocean below continues to push upward, and the flow doesn't stop. Over hours, or maybe days, more and more water escapes. Not just from one spot, but from a system of fractures spreading like veins across the icy shell, it becomes a cascade. At first, some of the material falls back. Gravity pulls it down as snow or ice, layering the surface with frost. But Europa's gravity is weak, only about 13% of Earth's. That means a large portion of the material escapes entirely. Launched into orbit around Jupiter, you might end up with a temporary ringy particle circling the planet, glowing faintly in reflected light. Some of the particles might drift into Jupiter's intense magnetic field, becoming part of its radiation belts, and some of it might simply vanish into space. Now think about the numbers. Europa's ocean is believed to contain more than twice the volume of Earth's oceans. It's a massive, global reservoir of salt water. If even a fraction of it escaped, it would be one of the most violent natural events in the solar system. But the visual spectacle is only part of the story. Let's talk about the science. As the water escapes, so do the secrets it held for billions of years. This ocean has been sealed away since Europa formed. It's been isolated from sunlight, protected from cosmic radiation, and largely untouched by external forces. Everything in that ocean, minerals, chemicals, perhaps even life, has existed in the same dark, high-pressure environment for eons. When the ocean escapes, it doesn't come out alone. It brings with it particles from the rocky seafloor, traces of chemical interactions, and if we're lucky, organic compounds, maybe even microbial life. Now, here's where things get exciting for science. A spacecraft nearby like the Europa Clipper could fly through the plume. Its instruments could sample the water vapor, analyze its composition, detect complex molecules, and search for signs of biological activity. We wouldn't need to drill. The ocean would come to us. In fact, this is already a part of the Clipper's mission plan. Scientists hope to catch Europa during one of these outbursts, though, ideally, a smaller one. They want a glimpse, not a flood. But what if this wasn't a glimpse? What if it was a full-scale breach? As more water escapes, Europa starts to change. The pressure inside drops. The ocean begins to recede. The shell of ice may collapse inward, triggering quakes and surface shifts. Without the heat trapped by that pressure, the remaining water may start to freeze from the top down and the bottom up. The ocean becomes thinner. Circulation slows. Hydrothermal activity near the core might shut down, and with it, the chance for life could vanish. Europa would become colder, quieter, less active. Eventually, if the loss is severe enough, the ocean could freeze solid. The moon that once held one of the greatest mysteries in the solar system would become another dead world, like so many others. But not everything is lost. Some of that water, frozen and scattered through space, might be collected by future missions. Tiny ice grains, floating through the void, could carry records of Europa's chemistry and, perhaps, its biology. These particles might preserve clues about the ocean's temperature, salt content, and pH, about the minerals near its seafloor, and maybe, just maybe, about the organisms that once lived in its depths. It's a strange paradox. Europa's greatest loss could be our greatest discovery. Because for all the danger a full-scale escape would bring to the moon itself, Cliff could give us answers we've been chasing for decades. Still, there's a cost. Europa wouldn't be the same. It would lose more than water. It would lose the dynamic forces that made it unique. The movement of its ice shell, the tidal heating from Jupiter, the interaction between rock, water, and heat that makes the moon so promising for life. In trying to observe its hidden heart, we might witness its slow death. And there's something haunting about that. Something beautiful, but tragic. Imagine standing on a nearby moon, watching Europa in the distance. A bright sphere, rimmed by a ghostly ring of ice particles. A frozen geyser, arching into space. The glow of distant sunlight refracting through mist that once belonged to an ocean. Europa, in that moment, would be both alive and ending, and the universe would be watching. Chapter 4. Titan. A world of alien familiarity. Imagine walking through a place where rivers flow, lakes ripple in the wind, and rain falls from cloudy skies. But it's not Earth. The rivers are filled with liquid methane. The lakes are seas of hydrocarbons, and the air is thick with nitrogen. This is Titan, Saturn's largest moon, and arguably the most Earth-like world we've discovered outside our planet. From the moment the Huygens probe descended onto Titan's surface in 2005, it rewrote our understanding of what a moon could be. Titan isn't just a frozen rock orbiting Saturn. It's a dynamic world with weather, geography, and even seasons. At nearly 5,150 kilometers across, it's bigger than Mercury, and beneath its hazy orange atmosphere lies a complex system of rivers, lakes, mountains, and perhaps even an ocean of liquid water hidden under an icy shell. Let's start with that atmosphere. Titan is the only moon in the solar system with a thick atmosphere, one that's even denser than Earth's, composed mostly of nitrogen with traces of methane and other hydrocarbons. This atmosphere creates a greenhouse effect that warms the surface slightly, though not nearly enough to melt water ice. The average surface temperature hovers around -290 degrees Fahrenheit or -179 Celsius, cold enough that methane and ethane can exist as liquids. This thick atmosphere also creates a constant haze, making it hard to see the surface in visible light. But with infrared imaging and radar, scientists have been able to peer through the clouds and map the terrain. What they found was astonishing: winding river channels, vast lakes, and even possible cryovolcanoes, volcanoes that erupt with icy material instead of lava. Titan's lakes, located mostly near the North Pole, are not water, but liquid methane and ethane. These lakes can be hundreds of kilometers wide. There's even a methane cycle that mimics Earth's water cycle. Methane evaporates into the atmosphere, forms clouds, and falls as rain, filling the lakes and carving out rivers. It's an active, living world, just with different chemistry. But the mystery deepens beneath the surface. Radar data suggests that Titan may harbor a subsurface ocean of liquid water mixed with ammonia. If true, it opens up fascinating possibilities for life, not on the surface, where it's too cold and chemically harsh, but deep underground, where conditions might be more stable and friendly. Even the surface chemistry is intriguing. Complex organic molecules, the building blocks of life, are forming in the upper atmosphere due to sunlight and cosmic rays breaking apart methane and nitrogen. These molecules slowly fall to the surface, creating a thick layer of organic-rich material. Some scientists think this could resemble what early Earth was like, before life took hold. So, is Titan just a cold copy of Earth, or is it a glimpse into an alien version of habitability? It's hard to say. What's certain is that Titan challenges our assumptions. It shows that Earth-like processes, erosion, rain, seasons, can occur with completely different materials and under very different conditions. It pushes us to expand our idea of what habitable means. NASA is betting big on Titan's potential. In 2027, the Dragonfly mission is scheduled to launch. This rotorcraft lander will arrive at Titan in the mid-2030s and begin flying from place to place, exploring dunes, plains, and maybe even the edges of methane lakes. It will carry instruments to study the chemistry of the surface and search for signs of prebiotic conditions. For the first time, we'll be able to hop across an alien world and see it up close, not just as a landscape, but as a system. One that may hold secrets to our own origins, because Titan doesn't just reflect Earth, it reimagines it. It's a place where the familiar becomes unfamiliar, where science fiction edges closer to science fact, and perhaps it's a mirror, one that shows us how strange and varied planetary evolution can be. So, as we look at Titan, we're not just looking at Saturn's moon. We're looking at a world that has lakes and rivers, skies and storms. We're re-looking at a place that tells us Earth, isn't the only world that can be alive in its own way. Titan reminds us that the universe is vast, not just in size, but in possibility. And as we prepare to visit it again, this time with wings, we step closer to understanding how nature builds worlds, not just like ours, but also unlike anything we've ever known. Chapter 5, The Final Frontier. Life beyond Earth, or life reimagined. As we leave behind Titan's cold rain and methane seas, a deeper question begins to echo. If life doesn't need Earth-like conditions to emerge, then what other forms might it take? For centuries, the search for life beyond our planet was guided by a simple assumption that life elsewhere would resemble life here. But as we explore moons like Europa, Enceladus and Titan, we begin to confront a far stranger and more expansive possibility. That life may exist in forms utterly alien to us, shaped by environments that seem inhospitable by Earth's standards. What if the universe is teeming with life, not as we know it, but as it has found a way to be? In the cold darkness beneath Europa's ice, hydrothermal vents may provide enough heat and energy to power ecosystems built on chemosynthesis instead of photosynthesis. Life forms that survive not by sunlight, but by chemical reactions. On Enceladus, the geysers spraying into space may carry the fingerprints of microbial life hidden deep below. And on Titan, with its thick atmosphere and rich organic chemistry, life might be something truly exotic. Not based on water at all, but on methane or some other solvent that can sustain molecular complexity in the extreme cold. These are no longer idle speculations. They are scientific questions driving real missions, real instruments, and real budgets. NASA, ESA, and private institutions are investing in spacecraft landers and orbiters that will return to these worlds with tools designed not only to take pictures, but to sniff out the subtle signals of biology, complex molecules, unusual isotope ratios, temperature anomalies, or chemical imbalances that shouldn't exist without something or someone keeping them that way. But this search forces us to expand more than just our instrumentation. It asks us to expand our imagination. Our very definition of life is Earth-centric, carbon-based, water-dependent, DNA-driven. But what if life can be silicon-based, or live in sulfuric acid clouds? What if consciousness can arise from something we haven't even conceived yet? Not neurons, but magnetic fields, plasma patterns, or quantum entanglement. We used to laugh at such notions. Today, we take them seriously, not as fantasies, but as frontiers. Even the term life might be too narrow. Maybe what we're really searching for is not just biology, but complexity, the kind that can adapt, evolve, and self-replicate, the kind that shows intent, even if it's alien to our senses. And if we do find something, some microbe under Europa's ice, some chemical whisper in Titan's haze, what does that mean for us? For one, it would end the age-old loneliness. We would no longer be the only known life in the cosmos, but it would also raise profound questions about our place. If life can arise in multiple locations independently, then maybe it's common. Maybe the universe is alive in countless ways, scattered like seeds across space and time. But if life turns out to be rare, if after exploring hundreds of planets and moons, we find only silence, then our responsibility becomes even greater. We are not just life, we are its caretakers, its storytellers, its only witness. Both answers are humbling. Both force us to reevaluate not just the universe, but ourselves. That's why missions to these distant moons are more than science. They are acts of existential exploration. They're not just asking, what's out there? They're asking, who are we? Because every discovery about alien worlds is also a discovery about the nature of life, of possibility, and of the universe's hunger for complexity. And if one day we find something out there looking back, a microbe, a message, or even just a pattern in the ice, it won't just be the end of a journey. It will be the beginning of a new chapter in human identity. A chapter where we are not alone. A chapter where Earth is not the only cradle, and life is not the only child. So we keep searching, not because we expect a particular answer, but because the questions themselves are worth asking. Because in the silence of the stars, even the faintest echo matters. And perhaps, somewhere beneath the frozen crust of a distant moon, a new kind of life is already stirring. Alien, unknowable, and yet somehow familiar. If this made you wonder what else might be out there, you're not alone. Subscribe for more stories that explore the strange, the silent, and the stunning possibilities of our universe. And let us know in the comments, do you believe we'll find life beyond Earth, or are we already it?